I'm going to talk through how to get the speeds that you need, to get the momentums that you need, to get the impulse that you're asked for in this impulse lab that I've asked you to do. Just going to free draw this. Hopefully it's not too messy. Basically what we've got is an inclined plane and a wall, or I changed what's down here, but some sort of thing down here. And we're going to pretend that they're frictionless, but we've got a cart on the incline. There's other ways to do it, but when I look at it, what kind of jumps into my brain is conservation of energy. We know that the cart, so we kind of got two phases. The cart goes downhill and crashes. I want to know how fast it's going when it gets down here and crashes into the wall. I'm going to call that V. From conservation of energy, it's a grade 11 topic. Depending how during COVID, when you had grade 11, sometimes this goes a little fast. Either way, it's a long time ago and we're not spending any grade 12 time on it. But the cart started up high and not moving. Well, up high might be a bit of a stretch, but it started not at its lowest point and not moving, so all its joules were gravitational. And then as it rolled down the hill, it got lower and lower, faster and faster. All those joules converted to kinetic. Gravitational energy, because we're close to Earth, we don't have to use that crazy one that we talked about in class the other day. It's just going to be mgh. Kinetic energy is always 1/2 mv squared. The m's are going to cancel. There's enough there that you can figure out the v that it had when it bonked into the wall. Once it bonks into the wall, then there's the second phase. I'm going to redraw it. So we've got our incline. We've got the wall. The cart's down here, touching the wall. And it gets kind of kicked back uphill because of that force interaction with the wall. It's not going to get kicked back off the wall at the same speed that it hit the wall at. And eventually, the cart ends up here at its highest point, and it stops for a split second. So for the second phase, this is I'll call this phase 2, the rebound. It starts off down low and moving, so it's got kinetic energy. And as it bounces off the wall and rolls back up the hill, it converts those kinetic joules back into gravitational. So the 1/2 mv squared, but this is the other v, equals mgh. The m's are going to cancel, and there's enough there that you can do some algebra and figure out the second speed. So, conservation of energy, if you know, so in the video you might have to do a little bit of pausing and rewatching. If you can figure out the height that it started off from, well, I got to be careful with this. If you can figure out the change in height, how high it started off with compared to how low it ended at, if you can figure out that change in height, that's the h that you'll put into here, and you can figure out how fast it's going when it cracks into the wall, assuming that it doesn't lose any energy to friction. Then, if you can figure out how high it bounces back up to, maybe we should call this h prime to show that the h's are different. If you can find the second height, then you can use that to figure out the speed it had as it bounced off the wall. Once you get those two speeds, then I think it's okay. From this first kind of phase, then we can get we can get momentum. So the initial momentum is mass times speed. From the second part, we can get the final momentum. It's mass times the second speed. And then once you get that, you'll have to be careful with vectors and directions. Impulse, capital J, is the final momentum minus the initial momentum. All right, I think that'll help with the lab. If I'm mistaken and you're having issues, just shoot me an email and we'll figure it out together. But that's kind of what we're looking for in the first part of the lab. The second part of the lab is you do some graphing, and the graph is a little bit ugly, but then just do some geometric calculation. What's the area under the graph? If it's a rectangular shape, what's the area of the rectangle? If it's kind of a trapezoidy shape, what's the area of the trapezoid? But this should get you started, and as always, email if you have any questions.